Okay, so today we're just going to be talking about matching through two different conditions, two different examples. One is with Hall's condition over here, and then another is going to be with something called the Gale-Shapley algorithm. So starting with Hall's condition, which is a theorem, so you may hear it called Hall's theorem. Because this is one of the examples involving matching, essentially we're trying to find matchings between groups. That's sort of the theme for this lesson. So first of all, with Hall's condition, our goal is to find structurally impossible matchings based purely on eligibility. So it's a little easier to understand with an example, so let's dive into that. So imagine you have a small tech department that's just trying to assign, well, that didn't copy over, right, hold on. That is not engineers. Okay. Imagine a small tech department trying to assign 4 software engineers to 4 specialized software projects. There's no rankings. Either the person has the specific skills required for a project or they don't. Pretty simple. Now let's say we have 4 people, and as luck would have it, they are only individually good at 2 things. So let's say Alice is good at front end and back end. Bob is also good at front end and back end. Charlie is good at front end and back end. And Dave is good at data science and security, so he sticks out. Anywho, we have 4 people, 4 different roles that we need to fill, that this tech department is trying to fill. So by Hall's condition, okay, that E should not be floating around there. Hold on. So by Hall's condition, we define a few things first. We define S, which is a subset. In this case, it is our group of 4 engineers, which means if you take the absolute value of S, that just gives you the size of the subset. Pretty simple. So in this case, it's 4. Next, we describe something called N, I'm going to call it N of S, or NS. That is the neighborhood. So in this case, NS represents all the options we can get from our subset. In other words, what is each person in the group able to offer, right? So we have a variety of skills, of options that each person offers here. We have front end, back end, data science, security, right? It's a variety. So if you take the absolute value of this neighborhood variable, if we take this quantity, absolute value of NS, that just gives you the total number of unique options available to that specific group of engineers. So we want to know, is there able to be a perfect matching for these 4 people to the 4 roles, given that we have their skills, we have 4 people, we have 4 roles. We just want to know, can you perfectly match each person to a role, given their skills? Well, Hall's condition asks us to do this first. We look at our set again, Alice, Bob, Charlie, Dave. We look at it again. Now let's say we pull an even smaller subset out of our already small group of 4. Let's say we just target Alice, Bob, and Charlie. Okay, we have 3 people. They are 3 people with tasks, with abilities. But look again, Alice, Bob, and Charlie are all good at the exact same 2 things. So what does that mean? These 3 guys are only good collectively at 2 things, front end and back end. That's all they individually and collectively are good at doing. So what this means, and I wrote it over here in case you forgot, front end and back end, that's the 2 things they are good at. So what does that mean? Well, if you isolate this little group of 3 from the bigger group of 4, that means our size of the subset is 3, because we're looking at 3 people here. And then the neighborhood size, in other words, the size of their skills they can offer, their options they can offer, right, is 2. The problem is, Hall's condition says you can only get a perfect matching if the size of your neighborhood is greater than the size of your people. In other words, for there to be a perfect matching here, these 3 guys have to have more than just 2 skills altogether. And we're not counting unique cases, right? Like Alice says she's good at front end and back end. Bob says he's good at front end and back end. But when we consider it from this perspective, we are looking at what skills they have in common. We are not counting individual cases. So for example, even though these 3 are all good at front end and back end, you cannot say, oh, we have 6 skills because each person has 2 skills. No, we're considering the ones that are sharing common as just one. So if they're all good at front end, that's one skill. If they're all good at back end, that's another skill. Therefore, we have only 2 skills that are in these 3 people's collective project pool. So the size of the people we're looking at, the group we're looking at, is 3, and the number of skills they collectively offer is 2. 2 is smaller than 3. Therefore, we cannot have a perfect matching, because in this case, the neighborhood size, the number of skills they can offer, is smaller than the number of people we're looking at. Okay? So this subgroup with absolute value of S equals 3, the size of the people, and the absolute value of NS, the size of the neighborhood, is 2. This means that Hall's condition fails because we were wanting to know if there's a perfect matching for these 4 people, but we literally just pulled out 3 people and Hall's condition already failed. So the rule of thumb is, if you pull out a smaller group of your large set to look at and it fails Hall's condition, then your whole group, your whole larger group, also fails Hall's condition. Therefore, for the entire group of 4, because of this smaller group of 3 not meeting the requirements, the entire finding a perfect matching for the entire graph is impossible. Okay, so that's an example of what it looks like when you cannot have a perfect matching. But what would an example look like where you do have a perfect matching? Well, let's go back to those 4 people again: Alice, Bob, Charlie, and Dave. Let's say Alice is still good at front end and back end, okay? She's still got the same skills. Bob, let's say he's now good at back end and mobile. Charlie is good at front end and mobile. And Dave, he just does data science. So I want you to notice here, this is an alternative case where we are going to be able to have a perfect matching. And I want you to look at one thing in particular. Notice here, no 2 people have exactly the same skills. So remember before, with Alice and Bob, or Bob and Charlie, or Alice and Charlie, you could say, oh, they're both good at front end and back end. But now, you don't see anyone who has the exact same pair of skills. So Alice is good at front end and back end. Bob only shares back end in common with her, but he has his own unique skill that Alice does not share. So if you took, say, this group of Alice and Bob, you'd immediately have 3 skills: front end, back end, mobile, and it's only 2 people. Therefore, your neighborhood size of skills offered is a lot greater than the smaller group of people you're looking at. That's the key. And Charlie and Dave, well, you might wonder, well, Dave only has 1 skill now instead of 2. Wouldn't that kind of mess up the Hall's condition? Not really, because you can also consider Dave as his own little subgroup. That would be a subgroup of 1 person, and he has 1 skill, right? So if you go back to that statement for Hall's condition, the size of the neighborhood has to be greater than or equal to the size of your group of people. So in this case, we have Dave, that's size 1 for S, and then his skill, NS, that's 1, okay? Greater than or equal to, it works. So let's delve into that a little more written out, shall we? So let's do a check, right? Because for Hall's condition to work, you have to be able to take any, like imagine you have a really big group. You should be able to pull out any smaller subgroup out of your larger group and still be able to fulfill Hall's condition. So let's do a group of 1 check. So again, with Dave, okay, the subgroup size is 1, so because we're only looking at Dave, so that's 1 person. And then the size of the neighborhood, remember, in this case, total unique skills, that is also 1. He has 1 skill, data science. Okay, does this satisfy Hall's condition? Well, let's see. NS, the absolute value of NS is greater than or equal to the absolute value of S if Hall's condition is fulfilled. 1 is definitely greater than or equal to 1. Therefore, this is okay. Now let's do a group of 2 check, right? Because remember, we're looking at smaller groups within the larger set to make sure that Hall's condition is still fulfilled even in those little sets. So if we pick out any random 2 people, let's say Alice and Charlie, okay? So just keep in mind, you can pick any other pair to check too, you know? Like even in group of one check, we didn't have to go with Dave just because he also has only one skill. You could literally just pick Charlie or Alice or Bob or anybody else. But that's just how the idea goes. So let's say for our example, we check Alice and Charlie. Okay, so the front end and back end, the front end and mobile, okay? So our subgroup, absolute value of S, is 2, okay? Because we are looking at 2 people. And what is the absolute value of their neighborhood? The size of their total skills offered? It's 3, because we have front end, back end. Okay, Charlie also does front end, so we do not double count that, and mobile. That's 3 unique skills, front end, back end, mobile, and we're only looking at 2 people. So the skills they offer is greater than the size of their group, okay? So again, absolute value of the neighborhood has to be greater than or equal to the absolute value of the group of people itself, the absolute value of the subset, right? Because, and just to clarify, why do we use S? Because when we're looking at a smaller group, it's a smaller set. Therefore, it is a subset of the larger group, of the larger set. So the absolute value of the neighborhood is greater than or equal to the absolute value of the subset for Hall's condition to be satisfied. And we look at 2 people, we see they have 3 skills altogether. This satisfies the condition, so it's okay. Now let's do a group of 3 check. Let's do Alice, Bob, and Charlie again. If you remember, this is the subgroup, this is the subset we looked at in the previous version of this example that failed and made us know there is no perfect matching available here. Now let's look at it again, right? Because we have a little more variety in their skills. So we have front end, back end, and mobile. Remember, we're not double counting any skills. So, yeah, this is the trio that failed Hall's condition earlier. That was a want, so, okay. Here we have a subgroup subset. Absolute value of that is 3 because we're looking at 3 people. And then the size of their neighborhood is also 3 because, again, front end, back end, mobile, no double counting. So that is the number of unique skills they collectively offer. So in this case, is the size of the neighborhood greater than or equal to the size of the subset? The subset, yes, because 3 is definitely greater than or equal to 3. So this is also okay. Therefore, because you see that all these little groups work, we know that Hall's condition must be fulfilled for this. And if you even wanted to take a look again, like let's say we considered all 4 of them, right? Is the size of the larger set able to fulfill Hall's condition? Well, we have 4 people, so that means the number of skills they offer needs to be greater than or equal to 4. Well, we have front end, back end, mobile, data science. That's 4. We're good. So you just have to have a little more variety such that Hall's condition cannot fail for any of these people, for any of these conditions here. So that is Hall's theorem in work. That is Hall's condition in work. So you see how we need to consider unique options, unique neighborhood sets in order to determine if we can perfectly match. Because see, in a case like this, we're just trying to match each person. We want to make every person happy with a role or whatever the specific context of the word problem is, right? We want to make sure no person is left behind when this tech department assigns jobs. So now you can see, in this case, you don't have as much variety in the skills offered, therefore it's not possible for there to be a perfect matching, right? Like just think about it reasonably. Alice, Bob, Charlie, in this first example's version, they're all good at front end and back end. So what could happen? Well, Alice might get front end job, Charlie might get the back end, so what's Bob gonna do? Front end and back end are already taken. And yes, in this case, we're considering that, we're assuming that they only assign 1 person per specific role. So Bob would be left out in that case, which is why this is not a perfect example. However, over here, when you have a little more variety in the skill sets, we could see maybe Alice does back end, maybe Charlie does front end, Bob can take up mobile because nobody took that up, right? It's not been assigned to someone yet, okay? So that's Hall's theorem. Now let's go into the Gale-Shapley algorithm. So Gale-Shapley is used to pair up 2 equally sized groups of people to get a fair matching. So one really good example of this is with college applications and college committees that evaluate those applications. So imagine that you have 4 college applicants and 4 evaluator committees, each with their own preferences. Now, because this is a very simple word problem, we are going to assume that every college can only take 1 person. Ridiculous, I know, but it works for this example. So I want you to think about this. If you're a college applicant, what are you going to do? You're probably going to start looking for the best. You're going to apply and go to your top pick of college, right? And if you get rejected from that college, you're going to go down on your list maybe to the second best college on your list, right? So your options as an applicant are going to get progressively worse because you might get rejected from the one you really wanted to go to, and then you have to just keep going down the list depending on who doesn't reject you. Meanwhile, for the evaluator, the applicant committee, right, the college committee, their options are only going to get better over time because they only reject people if they find someone better than that person that gets rejected. So that's an important concept for this example. So let's say you have 4 people. Yes, we're dealing with 4s again. Let's say you have Amy, Ben, Chase, and Dave. Let's see. Yeah, could be the same Dave from the example earlier. He was struggling to get a perfect matching, so he decided to apply for some colleges. Let's go. So you see here, Amy, Ben, Chase, Dave, these are all the college applicants. They each have their preferences, their top picks of colleges, right? Amy's top pick is college 1, Chase's top pick is college 2, right? But then let's say the colleges receive all these applications. Now they also have their own preferences. You know, college 1 prefers Ben over Chase, college 2 prefers Amy over Dave, etc., right? So what is this algorithm going to do exactly? Well, if you remember from the last video when we talked about the graph coloring algorithm, the greedy coloring algorithm, remember it always stops from your top and then works its way down depending on what works when you're trying to find a coloring solution for your vertices, etc., depending on what they're adjacent to, right? You're starting from the top and working your way down. So that's kind of a similar case for this algorithm in the sense that, well, it'll be easier to see with an example. Also, let's assume for this problem that every person is only able to go to 1 college a day, so that's why we break this up into a few days. So let's take a look at what happens on day 1. So day 1, all these applicants are going to go to their top college first. So Amy and Ben, where are they going to go? They're going to go to college 1. Chase and Dave, they're going to go to college 2. But remember, in this example, the colleges can only take 1 person. So there's a little competition here. So now we need to consider the college preferences. Okay, college 1, what do they prefer? Ben or Amy? It looks to me that college 1 prefers Ben over Amy. So what does that mean? Amy's going to get rejected. Now what about college 2, Chase and Dave? Also a little competition. What is college 2's preference? Well, it looks like Dave is preferred more than Chase for college 2. Okay? So what does that mean? Chase is going to get rejected. So at the end of the day 1, we have Ben in college 1 and Dave in college 2. Meanwhile, Chase is a little frustrated, a little confused. Amy might be sad. It's okay. We move on to another day. Day 2. Now, because Amy and Chase have gotten rejected from their top pick, they're going to go down their list, okay? So Amy's next pick is college 2. So that's why she goes to college 2. We don't know if she'll stay there yet. Chase, his next pick, his number 2 pick, is college 1. So he's going to go to college 1. Now, is he going to stay there? We need to see. Well, let's take a look at the college list. Between Ben and Chase, who is preferred? Well, it actually looks like, despite college 1 being Ben's, despite college 1 being, where is it? Let's see, Ben and Chase. Looks like college 1 prefers Ben over Chase, so looks like Ben is actually pretty lucky. He doesn't get rejected, he just stays put because Ben's been here since day 1. So Chase is going to get rejected from college 1. Oof. Now what about college 2? Dave and Amy. Where does college 2 stand on its preferences? Well, it turns out college 2 actually prefers Amy over Dave. So in their eyes, Amy's a better applicant. So they're going to reject Dave, who's confused because he was there for day 1, right? But now he's rejected. So at the end of the day, day 2, We have Ben in college 1 and Amy in college 2. Chase is getting angry because he's just been rejected for 2 days in a row. Well, I know. And then Dave is just sad because he thought he was going to be able to stick around in college too. Okay, but again, we move on to another day. Now, we have Chase and Dave to deal with. So because Chase got rejected from 2 and 1, from college 1 and college 2, he's going to go to his next pick, which is college 4. Okay, so we're going to see Chase in college 4. Now, what about Dave? Well, he got rejected from his top pick of college 2. So he's going to go to the next pick, which is college 3. So let's see how that goes. Oh, looks like nobody's competing for spots anymore. Everyone has a college. So there's no competition here, right? We don't have multiple people in a college. So we don't have to do the whole rejection thing that we were doing for day 1 and day 2. So there's no competition here. Every college evaluator picked 1 student for each college. So now everyone is happy, right? This is how the Gale-Shapley algorithm works. It wants to get a fair matching because, ideally we don't have to go through a ton of rejections to the point that everyone ends up in the college they didn't want to go to or that was on the bottom of their list. That's what this Gale-Shapley algorithm tries to help prevent, is only doing as many rounds as needed until you get a fair matching between both parties. In this case, both the applicants and both the evaluators. Yeah, so everyone should be happy here. Ben definitely should be happy. He got in his top pick, so he better be happy. Okay, so that was a pretty straightforward example for Gale-Shapley. So just to wrap it up, between the matching concepts, we have Hall's condition, where you're going to look between the options that your group offers. In other words, you're going to consider the size of your group and also the neighborhood of what your group offers in order to determine if you can get a perfect matching. That's Hall's condition. And then for Gale-Shapley, you're going to try to get a fair matching by pairing up 2 equally sized groups of people or things, and with that, having the hope that everyone gets a matching with something of the other group, right? Applicants to colleges or college evaluators to applicants. Yeah, so that pretty much wraps it up for matching. I think for the next lesson, I'll be talking a little bit more about paths and walks and things of that nature. But yeah, this is just a little heads up to do with an extension of graph theory and a little more algorithms with word problems. So yeah, before we call it a day on this, do you have any questions about either Hall's condition or Gale-Shapley? And by question, I similar to the other video, I don't mean why is it called Gale-Shapley. I think it's because of the people that invented it. That seems pretty straightforward. Correct me if I'm wrong. For Hall's, I'm not sure on that. I would hope they named Hall's condition personally after a person and not after the cough drops. That would really suck. But they're both pretty cool principles. So yeah. What's your question?
So what's the actual, like, is there any practical use in the reality?
Like with these word problems, these could very well be real examples that you deal with in a real world scenario, right? So Gale-Shapley, it could be helpful for a case like this where let's say you have college applicants, college applications, evaluators, or even something else, for instance, medical students and trying to find residency at certain hospitals. That could be another example. Is really, both of these are matching approaches that you can use, matching strategies. And the goal of matching, more generally speaking, I believe is you're just trying to find a fair matching between both parties, right? In this case, you have college applicants and college committees. You want there to be a fair matching so that, college applicants don't end up going to the worst college because they didn't get matched sooner, or evaluators have to keep rejecting people to the point that it just gets exhaustive. And then similarly with the Hall's condition example, if you have different roles and you can only assign one person to each role, you want to make sure ideally that everyone's happy and nobody feels left out. So matching in a sense is really just trying to pair people together based on eligibility and other qualities. But there's definitely more examples than this. Matching by itself, I think, is just a good way to systematically look at groups and try to pair them together, if that makes sense. Any other questions? Okay, I think that pretty much wraps it up. So, yeah, till next time, I'm gonna drink my water.